All right, today we're going to fire up what I call the exponential engine. We're diving deep into the hidden math that's behind some of the biggest, most incredible changes in our world, from the phone in your pocket to, well, the future of everything. Let's jump in.
So, let's kick things off with a pretty mind-bending question. Seriously, think about it. How is the phone you're holding right now literally millions of times more powerful than the massive computers that took us to the moon back in the 70s? It just sounds impossible, right? But the answer, it actually comes down to one single, incredibly powerful idea.
You see, the secret isn't some slow, steady, step-by-step improvement. No, it's something way more dramatic. The answer is an exponential function. This is the mathematical rocket fuel that launched us from computers the size of a room to supercomputers that fit in the palm of our hand.
So let's meet the star of the show, the exponential function. It looks like this. F of x equals a times b to the power of x. Now think of a as your starting point, kind of like the launch pad. But the real engine, the part that creates that explosive growth, is b, the base. That's our growth factor, and it's what decides if we get a gentle curve or a vertical blast-off. Okay, so to really understand how this works, we've got to look at its DNA. And for that, we look at the simplest version, the parent function. Y equals b to the x. Every single exponential graph you will ever see is just a modified version of this basic blueprint. You get this parent graph, you get them all.
And here, you can literally see the power of that b value in action. Just look at the difference between y equals 2 to the x, y equals 3 to the x, and y equals 4 to the x. See how much steeper the curve gets as that base number gets bigger? That growth becomes way more explosive. That right there is the exponential engine kicking into high gear.
Now the cool thing is that every parent graph, no matter what its base is, shares the same core features. It's like they're all related. They all cross the y-axis at the point 0, 1, every single one. They also have a horizontal asymptote at y equals 0. Think of it like an electric fence or a floor the graph gets super close to, but just never touches. And because of that floor, the range, all the possible y values, is always positive, always greater than 0.
So now that we've got the parent's DNA figured out, we can start to have some fun with it. We can start shifting it, flipping it, basically transforming the graph to model all kinds of different situations. Let's see how that works.
All right, let's walk through our first one together. We've got y equals 2 to the power of x minus 1 plus 3. Now, I know it looks a little complicated at first, but if you look closely, you can see our parent function, y equals 2 to the x, just hiding in there. All the other numbers are just instructions telling us where to move it.
So, here's the game plan. Step 1, we spot the parent function. Y equals 2 to the x. Easy enough. Step 2, that x minus 1 up in the exponent, that tells us to shift the whole graph 1 unit to the right. And step 3, that plus 3 hanging out at the end, that tells us to just lift the whole thing up by 3 units. Simple as that.
And this brings us to a really important point. That vertical shift, that plus 3, doesn't just move the curve, it moves the floor, it moves that horizontal asymptote. So while our parent graph had its floor at y equals 0, our new graph has a new floor at y equals 3. This is a super critical detail, so keep it in mind.
Okay, you ready to level up? Let's take a look at y equals negative 3 to the x plus 4. See that little negative sign out front? That's a total game changer. It's about to flip this whole graph upside down and completely change how it behaves.
So let's break this one down. The parent is y equals 3 to the x. That negative sign reflects the entire graph over the x-axis, flipping it. Then the plus 4 shifts that flipped graph up by 4 units. So what does that give us? Well, we get a new asymptote, a new ceiling, this time at y equals 4. And that means our range is now all the y values times less than 4.
All right, now for a really important part. Let's talk about the common traps people fall into. I mean, knowing the rules is one thing, but knowing the mistakes to avoid, that's what really makes the difference. Let's go over a couple of big ones.
The number one mistake by far is forgetting about the asymptote. People do a great job shifting the graph up or down, but they leave that invisible floor behind at y equals 0. You gotta remember, the vertical shift, that plus c value at the end, is your new asymptote. The asymptote moves with the graph, always. And that first mistake leads right into the second one, getting the range wrong. The range for one of these functions is never all real numbers. It is completely 100% tied to that asymptote.
The graph is either entirely above the asymptote, making the range y greater than c, or if it's been reflected, it's entirely below it, making the range y less than c. It's that simple.
So now that we've got a handle on the mechanics, let's bring it all full circle. It's time to connect these graphs and equations back to the real world. Remember that supercomputer in your pocket? Let's finally see exactly how this math made it all happen.
This right here is Moore's Law. It was a prediction made way back in the 1960s, and it's been shockingly accurate for decades. It basically says that the number of tiny switches, transistors, we can fit on a computer chip doubles about every 2 years. That's not steady, linear growth. That's a perfect real-world example of y equals 2 to the x, and it's the engine that has driven our tech forward at such a crazy speed.
And the result of all that doubling, it's just staggering. We've gone from a few dozen transistors on a chip in the 70s to, today, well over 100 billion. That is the raw power of the exponential engine. And that is exactly why your phone is a supercomputer.
So that leaves us with a final question. What's the next exponential curve that's going to completely reshape our world? Is it going to be in artificial intelligence, maybe renewable energy, or some field that we can't even imagine yet? The exponential engine is always running, and now that you understand how it works, you have a brand new lens to see the future.